Hello folks, Mr. Chandler here to talk today about torque and rotational motion, Unit 5 in AP Physics 1. Let's get right to it. Starting off, I want to talk about the difference. We mentioned this a little bit in class on, what was it, Friday, I guess, and now I'm going to dive a little deeper into this. So we have rotation versus translation. Let's define our terms here. So we, again, talked about this on Friday, but we have displacement. We know that displacement in linear motion, which we call technically the translational motion, is the same thing. We call that delta x, right? And of course, here's my handwriting. Delta x, that's displacement change in your position. It's measured in meters, right? And then we mentioned in class on Friday that the angular, the rotational version of that, right? Because we're not going to be going from A to B, right? We're going to be spinning sometimes spinning in place maybe. And so the rotational version of that is delta theta, and we call it angular displacement, right? And it's describing how much we spin around in a circle. Okay, so if we had a wheel, right? You had a wheel and it starts to rotate like this, and if it spins around one complete time, one revolution, right? We'd say that was 2 pi radians of revolution. So if it spun around 3 times, it would be 6 pi radians, right? So we're going to be measuring the displacement of things, how much they spin, okay? Not going from A to B, and we're going to measure that in radians, and we're going to call that angular displacement. The same thing is true for velocity. And velocity, which was v, of course, and that was an object's change in position divided by the time it took, and that was measured in meters per second for things moving in a straight line, or what we call translational or linear motion. And now we're going to have angular velocity, and we're going to call this omega. And it's basically a little W with little wings on it on the sides. It's the exact same thing. Instead of saying how fast an object is moving from point A to point B, right? Oh, the person is running at 5 meters a second or whatever. Now we're going to say, oh, the thing is spinning at a certain speed, and that equation for this is going to be instead of delta x over time, it's delta theta over time, or angular displacement over time. Now time is again special. Time is scalar. It doesn't have any direction, anything like that. So time is something that can be used in both translational motion and in rotational motion, and it doesn't make a difference. Time is time. All right, the units here are going to be radians per second. Radians per second, just like meters per second. Okay, and again, it's how fast a wheel is spinning. So if this wheel that I had up here, let's make little spokes for it or whatever, okay? If this wheel, all right, if it were spinning around, and if it completed, let's say it completed 5 revolutions. So 5 revolutions, 5 times around, is going to be equal to 10 pi radians, right? Because 2 pi radians for every 1 revolution. If it did that, and let's say it did it in, 2 seconds, divide that by 2, and we get what? We get 5 pi radians. So we get 5 pi radians per second, right? So that would be the speed of the wheel, right? It's completing 2.5 revolutions every second, okay? We have acceleration. We know that acceleration is the change in the speed with respect to time. And for translation or linear motion, we said that's the change in our velocity divided by the time, and it was measured in meters per second squared. Well, the angular acceleration is the exact same thing. The letter for it is alpha, so it's kind of like a little fish-looking thing. The Greek letter alpha. Angular acceleration, instead of it being how fast you speed up or slow down running in a straight line, is how fast you speed up or slow down while you're spinning, right? So if this wheel had started from rest and it got to a maximum speed of 5 pi radians per second, but it did that in 5 seconds, divide the speed by the time and say, okay, well, it started from 0, right? So we say the change in our angular velocity was from 0 to 5 pi radians per second. Divide that by the time it took. Let's say it took 5 seconds, okay? And then our angular velocity, the 5's cancel out, is just pi radians per second squared. So we have an acceleration of pi radians per second squared. And that's going to be the units for angular acceleration, radians per second squared. So again, it's the exact same concept as everything you learned before, except instead of going from point A to point B, going in a straight line through space, now you're just spinning, right? You're rotating, okay? Every concept is the same, except now you're rotating. All right, let's continue talking about how we're going to connect these two things. So the equations can also be converted in the exact same way. Like, they just have different symbols. The concepts are the same, except that you're spinning instead of moving through space, right? So, for example, the equation delta x equals v naught t plus 1/2 at squared, very common equation we use a lot of the time in the first semester. And let's see, it's going to become, well, delta x, I'm going to change color here. I think the red is okay, but I think white's probably better. So let's see, in color, let's go to white, see if this works better. So the delta x becomes what? Well, the delta x is displacement, so if we're spinning in place, that's going to be delta theta, right? We call that angular displacement, and that's going to equal v naught t. Well, then v is velocity, but we have angular velocity now. That becomes omega naught, our initial angular velocity. Time doesn't do any time. Time is still time. Plus 1/2, that doesn't change. A, that's acceleration, but now we're spinning, so it's angular acceleration alpha, and then t squared. Right? And it's the exact same thing. You can do this with every equation. You just convert all the linear stuff to the rotational stuff, and you're good to go. As long as you have the data, plug the numbers in, you solve, there's no big deal. All right. So that, whoops, I should have wrote that. Can I move this up? Is that possible? I don't know. If I use the mouse, maybe. Let's see. Can I? No, I can't. Okay, I'll just rewrite it again. All right. Anyway, let me erase this and move it out of the way because I want to do an example problem with you real quick. So let's write this up here. So this is telling me delta theta equals omega naught t plus 1/2 alpha t squared. Okay, so let's do an example problem real quick. So we have a wheel, say, and it starts from rest, and it begins to spin with an angular acceleration of 3 radians per second squared. How long will it take the wheel to complete 50 revolutions? All right, so what are we given? We're giving an initial velocity, starts from rest, so we know this guy. We know that, let's see, angular acceleration of 3 pi radians per second. We know what the alpha is. We know that. And we know how many revolutions it makes. So we know delta theta, right? It's going to go around 50 spins. And so we're going to look for t. We're going to find t. Well, now there's 2 t's in here, but it's okay because we start from rest. So this whole term here will become 0, right? Because the initial angular velocity was 0. This whole term will go away. And so we're going to be left with one unknown variable, our t. We have alpha. We have delta theta. We're good to go. We just got to convert. What is 50 revolutions in radians? Right? We cannot plug in 50 for this term here, right? That's not going to work, and it must be in radians. So we're going to convert. So it's going to teach you how to convert. Here we go, real quick, okay? 50 revolutions. We're going to start off with that. Dimensional analysis. You shouldn't have learned this in chemistry class, but in case you forgot, this is how we do it. We make a little T chart. I start off with a unit I'm given, and I think, okay, I want to go to radians. So I say, okay, well, how would I convert from revolutions to radians? Well, in one revolution, there are 2 pi radians, right? And so the revolutions will cancel. One upstairs, one downstairs, right? They cancel out. And now I'm left with the unit I want, which is radians. So then I multiply the numbers across the top, and I'll divide by the numbers on the bottom. So easy. So 50 times 2 is 100. Leave the pi alone. We don't actually multiply by pi. Just leave it as pi. So 50 times 2 is 100. Times pi is 100 pi radians. Divide that by 1, but dividing by 1 doesn't do anything, right? So it just doesn't, divide by 1. Okay, done. 100 pi radians. So 50 revolutions is 100 pi radians. Now we have our displacement. We have that. All right, so now we're going to plug in our thing and we're going to solve. First, we're going to solve for t. I'm going to rearrange my variables first. So I'll take this equation up here, and I'm going to multiply by 2 both sides, get rid of the half. So I'm going to get 2 delta theta equals alpha, equals alpha t squared. And I'm going to divide by alpha, both sides, right? And then I'm going to just take square root of both sides. So I'm left with square root of 2 delta theta over alpha equals t. Everybody see how I did that? Hopefully, feel free to rewatch the videos as many times as you need to. There we go. Now plug in our numbers. So we're going to take our 100 pi into delta theta. So it's going to be the square root of 2 times 100 pi divided by our alpha was 3. And that's going to be our time. So on the calculator, and I should download that. Do I have that? Let me see if I have it. I don't have it on here. Okay, only my work computer. Anyway, so take our calculator and try to practice on your own here at home and take the square root. 200 pi divided by 3. And I'm getting about 14.5 seconds, roughly 14.5 seconds. And that's how long it's going to take me to do that. If I accelerate at that rate, All right, cool. So there we go. That's one example. Let's move on. Connecting linear and rotational motion. All right, so displacement, we know we have our delta x for linear and delta theta for angular or rotational. Okay, now what if we have a situation where a problem might ask us, hey, here's the linear displacement, but what if I want to convert that to an angular, or here's the angular, I want to convert it to linear. Very simple to do. I'm not going to go through why this works or how, although you can probably figure it out on your own. It has to do with the circumference of a circle. But the way it works is this. If I want to convert between these two, all I have to do is do this. I say, okay, well then delta x will equal delta theta times the radius r. That's it. For velocity, if I want to convert to linear velocity, I take the omega multiplied by r. Or the angular velocity times r, whatever the radius is of the object that's spinning, and that'll give me the linear velocity. For acceleration, same thing. Alpha, nope, no, not alpha, my bad. A equals r alpha, right? So the reason why this works, I'll go real quick, is because if you have a circle, right, and this doesn't make sense, it's okay, but we know the circumference of the circle is 2 pi r, right? 2 pi r, where r is the radius of the circle. So this is r, right? The radius of that circle. Well, if you imagine that circle, you know, if you took one revolution around it, right? One trip around that circle, okay? And how far would you go? Well, you could take that circle, right? And just kind of, if it were like a big tube, and just lay it out flat, straight, in a straight line, it would, how long would it be? Well, it would be 2 pi r meters long, right? That's how long that circle would be. Well, then if r was, say, 1 meter, if this r were actually 1 meter, right, then this would be 2 pi times 1, and so that my delta x would just equal the 2 pi, right, which is the angular displacement. If the radius were, say, 3, right, then that one revolution would be 2 pi times 3. And so the same thing over here, the r will become 3. So it works out just like that, right? All you gotta do is multiply by the radius, and you can convert from the angular version of the thing to the linear version of the thing. It works the same way for velocity and acceleration. If that didn't make a ton of sense to you, it's not that big a deal, so don't worry about it. Just know, but you do need to know what these equations are. You need to know this, you need to know this, and you need to know this. All right, so you need to remember those. Let's practice. Oh, graphing, right? I forgot. Okay, so remember graphing? Remember how that works, right? Remember that the a position versus time graph, the slope would equal velocity, and then of course a velocity versus time graph, the slope would equal acceleration, area under the curve would equal displacement. Okay, guess what? Just like with the equations, graph stuff works the same way too. So I had an angular displacement versus time graph. Guess what the slope would equal? You can see it there on the screen. It does equal omega, the angular velocity. If I had a angular velocity versus time graph, the slope would equal the acceleration, and the area under the curve would equal the angular displacement. All right. So everything works exact same way with graphs. Just put the word angular in front of it. Angular velocity, slope, angular velocity versus time graph is the angular acceleration, and the area under the curve is the angular displacement. Same thing is true for an angular acceleration. I didn't put it on here, but angular acceleration, if you remember, an acceleration versus time graph, the area under the curve was the change in velocity. That same thing works for angular acceleration time graph. I've never really seen one of those though, but everything works the same. It's all the same. You just put the word angular in front of it. All right. Let's try an example problem. A large wind turbine, typical of the size and specifications of a turbine that you see in a modern wind farm, has 3 blades connected to a central hub. The blades are 50 meters long and rotate at 10 RPM. That's revolutions per minute. What angular speed v does the speed correspond to, and what is the speed? It should be angular speed omega. I guess they couldn't put, the formatting is weird. It should be angular speed omega. And then what is the speed v of at the tip of the blade? What is the speed of a point 25 meters from the hub? All right, so we're going to break this down and solve each part. And you should work along with me, okay? You should pause the video right now and see if you can solve it yourself, but you can do that and check with me. So what do we know? We know that the blades are 50 meters long. From the central hub, the axis of rotation, so R is 50 meters, right? R is 50 meters. That's how long to the tip of the blade. They're rotating at 10 RPM, that's revolutions per minute, and we want to find the angular speed of the blade and the linear speed of the blade, a linear speed at the tip of the blade. All right, so we got to convert this RPM to radians per second first. That's the RPM is not going to work for us. Got to convert. How do we do that? We'll start with the unit we're given. That's revolutions per minute right? And we know that one revolution, so annoying. One revolution is 2 pi radians, so I'm going to convert that first, 2 pi radians. So the revolutions cancels the revolutions, right? And now I got to get rid of that minute to get the seconds. So that's easy. I know that 1 minute. Notice I'm already I'm up top now, right? I'm upstairs because the minutes over here is downstairs, right? It's revolutions per minute. So the minutes are downstairs over here. So I got to put minutes upstairs over here so that they cancel. Well, how many seconds in a minute? Well, 60 seconds in a minute, right? 60 seconds. So the minutes cancel. Now what am I left with? Radians per second, right? That's what I wanted. So I'm going to multiply across the top. So 10 times 2 is 20. Times pi is 20 pi. Divided by 60. Well, 20 over 60 is a third, right? So I'm going to get 1/3 pi. So this is going to be 1/3, or 1/3 pi radians per second. And I'm running out of room, so I'll just write over here radians per second. Hopefully you can see that. Okay. 1/3 pi radians per second. All right. You probably you want to leave pi alone. We don't want to multiply by pi. I mean, yeah, pi is 3.14, 159, whatever. We don't want to do that, right? Just leave pi as pi. It makes the math much easier. Okay, what is the angular speed? All right, well, no problem. Well, now we know that these things can do that this many revolutions in 1 minute, and we just calculated the speed. We didn't even realize it. But if we're doing 10 revolutions in 1 minute, then that means we must be going at 1/3 pi radians a second, right? You think about it, if you multiply that speed by 60, what would you get? You'd get 60 over 3 pi, which is 20 pi radians, which is 10 revolutions. So without even realizing it, we just calculated the angular speed. So there you go. You're welcome. Super cool. Okay, so it's going to be 1/3 pi radians per second, right? Yeah, the other way we could have done that was we could have said, okay, well, we'll do, you know what, I'm not going to do the other way because the other way is too long and it's stupid. So, all right, linear speed. Well, that's no problem. We had the angular speed, 1/3 pi radians, so we know how to convert. We just learned that V equals R omega. Well, omega is 1/3 pi. V is 50 meters, so, excuse me, R is 50 meters, the radius is 50. Omega was 1/3 pi. Radians per second. So I'm going to multiply these. So 50 over 3 pi. 50 pi over 3 is going to be my velocity. Now, for linear velocity, I am going to multiply by pi because you don't really talk about. It makes sense to leave pi as pi when you're referring to radians and radians per second because radians is measured in pi, right? It's 10 pi, 5 pi, 2 pi. But for linear velocity, you wouldn't tell someone, like, hey, how fast can you run? Oh, I can run 3 pi meters a second. Like, wait, 3 pi, seems like 9 something? Like, you wouldn't leave that in there. You would just tell them the number, right? So we're going to take that and do it now. So 50 times pi divided by 3 is about 52.3.4. So V is about 50, I'm just going to round it to a whole number, so 52 meters per second. Okay. That's how fast this blade is spinning at the tip, right? But now we want to find out what is the speed at a point 25 meters from the axis. Okay, so now our R is smaller, right? Now, so when we go to calculate this here, right, we're not going to use 50, we're going to use 25 because now we're at that point A in the picture. We're not on the tip. R isn't 50, R is 25. So we're going to do the same thing. V equals R omega, but now R is 25 because we're not all the way out on the tip of the blade, right? We want to know what the speed is somewhere closer, 25 meters away. Omega, though, is still 1/3 pi, right? That doesn't change. Multiply those across, so we get 25 pi over 3. And I'm gonna go ahead and actually, multiply by pi because, again, now we're talking about linear stuff. Maybe about 26, which makes sense. It should be half, right? It should be about half of what we had, and it in fact is. 26 meters a second, right? It's half that speed. Okay. All right, so we found, if you think about up here, let's go back and talk about this, 10 RPM. It's telling us, think about the units for a minute. Revolutions per minute. That is the speed, right? It's telling me how many times around it goes, 10 times per unit of time. It's per minutes, right? So it's actually telling us a speed. It's just not the right units of speed. So we have to convert that. So when we converted revolutions per minute to radians per second, that's how we found angular speed, right? We didn't use any other equation. We just did it that way, and that's the easiest way to do it. All right. quick check here. Rashid and Sophia are riding a merry-go-round that is spinning steadily. How long have I been going for? Didn't tell me. It should tell me. Somewhere it tells me. Oh, there it is. 20 minutes already. Okay. Rashid and Sophia are riding a merry-go-round that is spinning steadily. Sophia is twice as far from the axis as is Rashid. Sophia's angular velocity is that of Rashid. All right, so pause it. Ask yourself the answer. Think about it. You're back. Okay, so the answer here, we're looking for angular speed. The answer is going to be the same. All right, it's the same speed. Where's my pen? The same. The answer is in B. Why the same? Okay, here's the deal, guys. This is actually relatively important. All right, so pay attention. I'm going to change color here because this background is white. So let me go back to red. All right, angular speed. Here's the center of axis of rotation. There's like the radius, right? I'm going to draw it through Rashid and Sophia's position. Let's say that 1 second later, Rashid is over here. That's R, and then Sophia's on the edge. She's here. She's S. Let's say we're rotating. It looks like it's rotating clockwise, so we're rotating this direction, right? Now I'm going to draw another line over here. You get the idea. It's going to be a straight line. Let's try this. There we go. Okay. Okay. Is this angle right here, imagine a clock arm, right? And it's going and it's sweeping out the angle. I say sweeping out the angle as it turns. It kind of goes, 1 degree, 5 degrees, 10 degrees. It's sweeping out the angle. Is the angle that is swept out from the original position to over here the same for both Rashid and Sophia? Is the angle the same? The answer is yeah, the angle is the same. Well, angular velocity, oh my gosh, omega is delta theta over time. So they had the same angle that they're sweeping out and the same time, right? I mean, they're on the merry-go-round. They're not running around. They're stationary on the merry-go-round. So as they move around, it rotates. The time is the same for both. So if the angle is the same for both and the time is the same for both, then they're going to have the same angular velocity. So the answer is in fact B. So that makes sense. So it's not about how far they go. It's about the angle that is swept out in that amount of time. How about this one? Exact same question, except we changed one word. We removed the word angular. So now it's just what's Sophia's speed relative to Rashid. All right. Pause it. Think about it. Okay, you're back. All right. So hopefully this time you said it is twice as much. Well, why is it twice this time and not before? Well, think about it. We're converting now to speed. That's linear speed. If they want you to think about angular speed, they will say angular speed. It will say angular. So don't assume, which does it mean? If it just says speed, it's linear. So this is linear speed. Well, linear speed V is R omega. Well, we already said they have the same omega, right? So Rashid and Sophia, same angular speed. Well, but Sophia's twice as far away, so she has double the radius. And so if this is doubled, right, times 2, and this is the same times 1, well then 2 times 1 is 2, so we're going to get twice the velocity. And there you go, twice the speed for Sophia. The further out you go, the faster you're going to be moving because you have a bigger radius. You're literally traveling farther. Think about it. Sophia, the linear distance she travels is longer than the distance that Rashid travels because she has a big radius. She's further out on the edge. This is why it's more fun, usually, if you like exhilarating things, to be on the edge of a, merry-go-round type situation if you're into that sort of thing. Torque. Last thing, we're almost done. I know it's been a long video so far. Hopefully you can pause it, and come back and watch at different times, but I want to cover this last bit. All right, so what is torque? Torque is the rotational version of force, right? So it's not called angular force. That might be too much. We call it torque, although you can think of it as angular force, I guess. There are 3 components of torque. Think about opening a door. Where do you push on the door? If you're going to leave my classroom, it's got that push bar, right? Do you push on it near the hinges, in the middle, on the edge? It really doesn't even matter. I don't know. So where do you push on the door? What angle do you push on the door at? Do you push it like straight out, or kind of like to the side, or towards the center, toward the hinges? Think about it. Well, look at this picture here. If I wanted to create the most torque, which is rotational version of force, right? So what did forces do? Forces, linear forces, right? They make things accelerate. They make objects, things accelerate. We can speed them up or we can slow them down, right? Well, if the door is at rest and we want it to rotate, right? We want it to spin essentially about an axis. We want to apply a torque. So we want to make this thing rotate. So if forces make things accelerate, then torque, they make things, can you say it? Angularly accelerate, right? They make things rotate. Angularly, is that even a word? I don't know if I'm going to write it. Accelerate, right? So if I want to push a thing in a straight line, I apply a force. If I want to rotate something, I need torque. All right, so where would I push on the door? And how would I push? If the hinges are here on the left-hand side of this door in the picture, where am I going to push and how am I going to push? Hopefully you're thinking, I want to push F1 because I want to do far from the hinges. You know this instinctively, that if I want to make the door open easier and more, without having to push as hard, I'm going to push on the opposite side of the hinges. Not right next to the hinges. That doesn't make sense. I got to push really hard then. Why? All right, well, here's why. All right, so these three factors, where to push, how hard you push, and the angle you push, they make up torque. So torque is, here's the equation for it, is Fr sine theta. All right, F, the force applied. R is the distance. Let's go through this. So F is the force you apply, right? That should be for, oh my gosh, this pen is garbage sometimes. That is the force. R is the distance from the pivot, or the spot where we're rotating around, so the axis of rotation or the pivot point, different words for the same thing, the hinge of the door in this case, from the pivot to the spot where the force is applied. Okay, this is supposed to be an F for force. Okay. So if I push them at F1, and the hinge is over here, that's where it's going to rotate, then the R would essentially be the distance from the hinges to the edge of the door, right? Because I'm pushing on the edge of the door. All right. And the angle, theta, is the angle between those two vectors, right? I'll talk more about that in a second. But that's the equation. It's given to you on the formula chart, so you don't have to memorize it. Fr sine theta. All right. So only the force that is perpendicular to the radial line provides torque on the object. So what is this radial line? I'll cover that in a second. But let's talk about units first. Units for torque are Newton meters, not newtons per meter. Students always want to say newtons per meter. No, it's not newtons per meter. It's just Newton meters, right? It's the force times the R, the radius. Newtons times meters. Newton meters. All right. So what is this radial line? The radial line is an imaginary line that is drawn, again, from the pivot point, from the axis of rotation, the spot where this thing's going to rotate around, to the spot where we apply the force. So in the picture drawn there on this, we're rotating this wrench, the radial line is from the pivot point drawn through the spot where the force is applied, and you see the R is the distance between those two spots. All right. Now, the angle theta is super important because students always, this is probably the hardest part, students mess up a lot. The angle theta, think about it. If you want to make a thing rotate, here's that door again, okay? If I want to make it rotate, I don't want to push it this way, right? That's not going to make it rotate. If this was just some object sitting on the ground, it might make it accelerate in this direction, but it's not going to spin, right? It's not going to rotate about an axis. If I push it right at the center like this, well, if I push it this way, same thing. I'm not going to rotate. If it has a hinge here, we call that a natural pivot point. It has a hinge there. I have to push it this direction or maybe this direction to get it to actually rotate about that pivot point. Pushing it this way isn't going to do anything. So imagine a radial line like that, right? If I push on it right there to the left like that, what's the angle between those two lines? We might say it's 180 degrees or we might say 0 degrees. Either way, it's fine because the sine of 180 is 0. The sine of 0 is also 0. So there's no component pushing it. If you push it like this, there's no component this way or this way to make the door actually rotate, right? So the component of the force that is actually making a thing rotate is only the component of that force that is perpendicular to that radial line. Okay, so again, let's look at this one more time. If I imagine I push it at an angle like, say I push it right here, and I push it in this direction, right? We could break this force component down, okay, to say a part of that component is this way, right? And part of that force is up that way, right? Well, this component right here isn't going to do anything to make the door rotate, right? Only this component here is applying a force in the direction that will cause a rotation. So the reason why we had that FR sine theta part, right? FR sine theta, that equals torque. The reason why we have sine theta is to get the component of the force vector that is perpendicular to this radial line, right? To make the thing actually rotate. So look at the picture here. See the little theta symbol there? There's a radial line as it continues through the point of application of the force. And then we want to find the component of that force that is perpendicular to the radial line. So if that's a triangle we're making, right, you can imagine here, let me draw so I can see it. Although I'm sure you can figure this out. But here's a triangle, right? Imagine this is here. And then so one component of the force is there. And one component of force is here. My beautiful lines. But we don't care about this one, right? That force there, that component doesn't do anything to rotate this thing. Only this component actually causes a rotation. Well, that's on the opposite side of this triangle, so we're going to be using sine, all right? So there you go. Let's practice now, okay? So this question I just asked y'all essentially, the four forces shown have the same strength, so and then the same magnitude of force. Which force would be the most effective in opening the door? So pause the video, answer on your own. All right, so hopefully it's F1, right? We don't want to push near the hinges. That doesn't make sense. We want to push far away from the hinges, F1. We don't want to push it at some weird angle. We want as much force being perpendicular to the radial line as possible. So F1 is going to be our best option there. All right, let's do an example problem. We're going to do two actually, then we'll be done. I know this video's been long, but again, hopefully you're welcome to pause it and come back. So hopefully you're okay. All right. What do you got? We got Ryan. He's trying to push open a stuck door. He pushes on the door a point 0.75 meters from the hinges with 240 newtons of force directed at a 20-degree angle away from being perpendicular to the door. And see the picture for reference. There's a natural pivot point, the hinges. Yep. What torque does Ryan exert? And how could he exert more torque? Okay. So we'll use that picture there. I might draw it again so I can write on it. Here we go. So what do we know? We know R is 0.75 meters. All right, we are pushing at a spot 0.75 meters away from the hinges. The hinges are the pivot point for the axis of rotation, and our spot we're applying the force is 0.75 meters from that, so that's our R. The force, F, is 240 newtons. That's how hard Ryan is going to push on the door. So that's the force. Now the angle is now the question is what's the angle, right? We know torque is F R sine theta, right? And so we got to be very careful. And this is where students go wrong. Because so far you're like, oh, it's easy. Torque is FR sine theta. They told us the force. They told us R. Let's plug the numbers in, right? Yes, but be careful. So let's draw this out. Here's the door. Here's the hinge. Ryan's going to push this way, right? At an angle. Now they're saying the angle is 20 degrees away from being perpendicular. In other words, look at the picture that from the textbook. If the 20 degrees... This light white arrow I just drew is perpendicular to the door, right? So they're saying it's 20 degrees from being perpendicular. So in other words, 20 degrees from here. This angle right here, God, I hate this pen, is 20 degrees. Okay. So think about this for a minute. I want the component of this force vector that is perpendicular to the door. Let's draw that. Let's get a different color here so we can see it better. Let's do red. So this force vector, the one in the thicker white line, it has components. It's going this way, right? Or I guess I'll just whatever you can do what I mean. It has components going to the right. It has components going up. Let's get yellow, I guess. Oh, green, sure that works. All right, going up. Which one of those is perpendicular to the door? Hopefully you can see it's green, right? The green arrow. Okay. So what angle do I actually need? Now here's the trick, guys, because they're going to give you angles in questions. You can't just use whatever angle they give you. If you solve this problem using angle 20 degrees, you're going to get it wrong. You have to think more carefully. And I would always recommend draw it out, all right? Because the angle we want here, the component we want is this green one here, this one going perpendicular to the door, right? Here's the radial line. All right, going along the door there, from the hinge of the door through the spot where we apply the force. So there's a radial line, that light green line. So I want this thick green line, the one that is perpendicular to that spot. Well, if I do sine of 20, I'm going to get this component up here, right? I don't want that one. So I'm gonna redraw this, not using what they gave me. I'm gonna use my own brain here and say, okay, well, this is the actual, triangle I want to think about. And if this angle up here was 20 degrees, that means that this angle down here is 70 degrees, right? And so what I actually want is a sine of 70, because that's the component of this triangle that is perpendicular to the door. So our answer for this torque is going to be F is 240. Oh my god, I hate this pen. 240. R is 0.75. Sine of 70 degrees, not 20. Hope that made sense. You're going to practice a bunch in class, but we really got to be careful about how to find the correct angle. That is the thing that trips students up the most. All right, 0.75 times sine of 70, and I'm getting about 169. Let's call it 170. 170, 169, whatever, Newton meters of torque. Okay, how could Ryan apply more torque? Well, push perpendicular to the door. Don't push at an angle, or go further from the edge of the door, or push harder, right? Those are the things you could do. Push harder, push at a better angle, push exactly perpendicular to the door instead of 20 degrees off being perpendicular, or move to the very edge of the door. Either way, you're gonna get you more torque. All right. Hope that makes sense. Watch this again if you need to understand what I'm talking about. It's very important to find the right angle. Last question. I know it's been long. I know. I'm sorry. There's a lot of stuff to cover. Revolutionaries attempt to pull down a statue of the great leader by pulling on a rope tied to the top of his head. The statue is 70 meters tall, and they pulled a force of 4,200 newtons at an angle of 65 degrees to the horizontal. What is the torque they exert on the statue? If they are standing to the right of the statue, is the torque positive or negative? We haven't talked about that yet. We will right now. All right, so let's do it. So let's draw a little picture. Always helps in these problems to draw a picture. I highly recommend you always draw a picture, because if you don't, it just things get messy. So here's the great leader. There was a picture I used to use in class of Saddam Hussein, if you know who that is, leader of Iraq back in the 90s. And they pulled down a statue of him kind of the same way. So we attach a rope to the top of his head, and we pull down like this, right? And it says that the angle, 65 degrees from the horizontal. Here, the horizontal is the ground, right? The ground's horizontal. So the angle here is 65 degrees right here. Okay. Statue is 17 meters tall, so this length here is 17 meters. Gosh, this pen is just so irritating. 17 oh my god, meters. Oh my god. Whatever. Okay, and what else do we know? And the force we're pulling on is 4,200 newtons. All right, down, right, trying to topple the statue. Okay. Anything else we know? No, we don't. We're going to find out what are the torque exerted. Okay, well, we know torque equation is F R sine theta. Now, okay, so we got to be careful. We know the force. That's 4,200 newtons. That's not a problem. What's R? R is the distance from the pivot point to the spot where the force is applied on the object that we're rotating. Well, you can imagine a statue. Again, it might have like a little a base where it's kind of connected to the ground. If you pull on the statue from the top of its head to topple it over, we're going to go ahead and assume that the hinge, the pivot points for the statue is going to be this base down here, right? So the pivot point is the feet of the statue, where it touches the ground. The spot where the force is applied is the top of the head where the rope is. So the radius, R, is 17 meters. So R is 17, force is 4,200. All we got to find is the angle. This is the hard part, right? We don't want, we got to make sure that the angle they're giving us is the angle we want. If not, we just got to be careful, okay? Now, so that means the radial line, that radial line is an important concept to understand about, is this line from the spot where the pivot point is, the base of the feet down here, where the yellow dot is, up to the center of the statue, up that way. That is the radial line, right? That yellow line I just drew. Okay. So we want the force component that is perpendicular to that line. If I find the sine of 65 degrees, that's going to be this component of the point. Think about this, right? I'm going to draw this out again. Here's the force component pulling down, right? The angle here is 65 degrees. If I do sine, right, of that angle, I'm going to get this vertical component here. Is that perpendicular to the radial line? No, it is not. I don't want to use that angle. Instead, I want to think about the other side. I want to say, well, hold on a minute. If that's 65 degrees, that means this side over here, this is 35 degrees, right? Oh, no, sorry, 25 degrees. Excuse me. 25 degrees, right? And then if I take the sine of this side, that's going to give me the opposite side, which is here. That thick yellow line I just drew, this side, right? And that's the side I want. That's the component perpendicular to the radial line, okay? So that's the one I want. You have to be careful about the angle. This is where students lose it, all right? This is when they get things wrong. Always double check. Sometimes the angle they give you is the angle you want. Sometimes you just got to use your brain to be like, okay, well, I got to draw this out and make sure, because, you know, sometimes the angle they give me, it's, you know, it isn't quite right. So always double check. But anyway, this one's just going to be, torque will be F is 4,200, R is 17, and now we know the sine of 35, not, sorry, 25, I keep saying 35, 25 degrees, not 65 degrees. And then we're going to get an answer. Make sure you're always in degree mode for these. 200 times 17 times the sine of 25. And I'm getting about 30,000. That's just 30,175 Newton meters of torque. What direction is that? Now, we haven't talked about direction yet, so real quick. Well, I'm going to rotate it this way, right? This direction. It's going to fall that way. Imagine a clock, okay? 12 o'clock. Oh my God, this freaking pin. 12, 3, 6, 9. Okay. If I'm at 12 o'clock and I rotate this direction, we call that clockwise, right? That's the same direction a clock hand would rotate. We generally call clockwise negative. It is a negative direction. And we generally call counterclockwise, so if we rotate the other direction, I should get a different color quicker than having to do this. If I rotate this direction, right, I'm going the opposite of a clock, we call that counterclockwise. Oops. Oh my gosh, come on, pen. We call that counterclockwise, and that's what we call positive. Sometimes we abbreviate this as CW for clockwise, and then CCW for counterclockwise. But anyway, counterclockwise positive, clockwise negative. So if this thing causes the rotation to be clockwise or negative, then the torque would be technically negative. Right? So it's a negative torque. Just means the direction that it causes the object to rotate in. Okay. All right, that's it. That's the last slide. There's more to come, though. Don't worry. There's a lot more topics: gravitational torque, equilibrium, Newton's laws. A lot more stuff to do. So sorry the video was so long, but again, hopefully you made it through. Quiz on Monday. Make sure you're watching this. It's not, 5 minutes. Well, I guess it's better than not watching it at all. But anyway, I'll see you on Monday. Have a great rest of your weekend. Bye.